Hey everyone, and welcome. We have this image of scientific geniuses like Albert Einstein as being, well, infallible. But what if the most amazing thing about him wasn't just being right, but also being profoundly, brilliantly wrong? Today we're going to dive into the mistakes that literally reshaped our universe.
Okay, so let's start with this quote from the physicist George Gamow, who was talking about a conversation he had with Einstein himself. Think about that. It's a powerful admission of a huge error from the guy who literally rewrote the rules of the cosmos. And believe it or not, this one single blunder is where our whole story really kicks off.
And that really gets to the heart of what we're talking about today. So, were these just mistakes, simple failures? Or were his doubts something else entirely? Were they actually pushing science to its absolute limits, setting up these incredible challenges that would take generations of physicists to figure out, and in the end, lead to some of the most profound discoveries we've ever made?
All right, so let's jump right in. We're going to look at three of Einstein's most famous objections, the moments where he looked at the absolutely mind-bending stuff coming out of modern physics and basically said, nope, no way, that can't be right.
Okay, so here are the big three. First up, he was convinced that gravitational waves, these actual ripples in space-time, just didn't exist. Then there was this huge problem with quantum entanglement, which he famously called spooky action at a distance. And, of course, that cosmological constant we just talked about. Each one of these was a huge "I don't think so" from a genius, and each one, ironically, kicked off its own scientific revolution.
All right, let's dig into that first big puzzle, Einstein's deep skepticism about the quantum world. He just could not get his head around how weird reality seemed to be on that tiny subatomic level.
And really, at the core of it all was this one thing: quantum entanglement. Think of it like this. You have two particles that become linked. They're like two sides of the same coin, forever connected. The moment you look at one and see its heads, you know instantly that the other one is tails, and it doesn't matter if it's on the other side of the universe. They act like a single system, no matter the distance.
So, back in 1935, Einstein and a couple of his colleagues came up with a thought experiment to show just how ridiculous this whole idea was. It's called the EPR paradox. Okay, stick with me here. Imagine you have a pair of gloves, one left, one right. You pop them into separate boxes and mail them to opposite ends of the planet. The second you open your box and see a left-handed glove, you instantly know the other box has a right-handed one. For Einstein, entangled particles had to be just like that. He was sure the information was hidden inside them right from the start. And this is the key, right? Einstein was basically saying the universe shouldn't be spooky. He believed that those particles had their properties set in stone from the beginning. He called them local hidden variables. As far as he was concerned, quantum mechanics was just incomplete. This whole spooky action thing was just an illusion because we weren't seeing the full picture.
So for decades, this was just a debate for philosophers and physicists over coffee. How could you possibly test this? How could you design an experiment to see if these hidden variables were real or not? It seemed absolutely impossible. But science is pretty clever.
And what a journey it was. Just look at this timeline. It all started in 1964 with a physicist named John Bell, who came up with this brilliant mathematical test. Basically, if Einstein was right, the results of an experiment would always stay below a certain number. But if quantum mechanics was right, they'd go above it. But then it took another 30 years, and these absolute pioneers like John Clauser, Alain Aspect, and Anton Zeilinger to actually build experiments sensitive enough to put the universe on trial. And the result? Oh, it was absolutely stunning. In 1972, John Clauser's experiment didn't just cross Bell's line, it completely shattered it. The result was what physicists call a 5 sigma discovery. Now, that's the gold standard. It means the odds of this just being a random fluke were less than 1 in 3 million. So the universe had been put on trial, and the verdict was in. Reality is spooky. It's just that weird. There are no hidden variables. That strange connection between particles is real. And on this one, Einstein's famous gut feeling was wrong. Okay, but here's where it gets really interesting. Because even though Einstein was wrong about the quantum world, his theories that were right, I'm talking about general relativity, well, they opened up ways to see the universe that he could never have dreamed of. And ironically, they ended up proving some of his other big ideas right.
Okay, so one of the wildest predictions from general relativity is this thing called gravitational lensing. The basic idea is that really massive objects, like galaxies, literally bend the fabric of space-time around them. And when light from something far away travels through that warped space, its path gets bent too. So a huge galaxy can act like a giant magnifying glass in the cosmos. And this quote from astrophysicist Devin Powell puts it perfectly. We can actually use this effect to map out stuff we can't even see, like dark matter.
By looking at how the light from a galaxy way in the background gets twisted and distorted, we can figure out exactly how much invisible stuff is sitting in the foreground. It's incredible.
And get this, that exact same principle, light being bent by gravity, is what lets us do something that sounds like it's straight out of science fiction. Take an actual picture of a black hole.
So the Event Horizon Telescope, or EHT, isn't just one telescope. It's a whole network of them, all across the planet, all working together to create a virtual telescope the size of the Earth itself. It's just mind-boggling. And in 2018, they aimed this planet-sized camera at a galaxy called M87, and they did it. They captured the shadow of its supermassive black hole. I mean, look at that. It's a direct, visual confirmation of one of the most extreme predictions of Einstein's theory of gravity. It turned his math into an actual picture.
Okay, so let's circle all the way back to where we started, that biggest blunder. Because this, right here, is where the story takes the most ironic and honestly, the most beautiful turn of all.
Just look at this. It's a complete 180. Einstein first stuck the cosmological constant into his equations to make them describe a universe that was static, one that wasn't expanding or contracting. Then, when Edwin Hubble discovered the universe was expanding, Einstein was thrilled to get rid of it. He called it a huge mistake. But then, fast forward to the late 1990s, and astronomers make a shocking discovery. The expansion of the universe isn't slowing down. It's accelerating.
So they needed something in the math to explain this mysterious force pushing everything apart. And what was the best tool for the job? You guessed it. The cosmological constant. The very thing Einstein kicked himself over for decades turned out to be an incredible, ahead-of-its-time idea. It's our best explanation for what we now call dark energy, this mysterious stuff that makes up almost 70% of our entire universe.
So what does this all teach us? What's the big takeaway here? Well, it shows that science isn't just a straight line from question to correct answer. It's messy, it's fascinating, and it's full of questions, doubts, and yeah, even huge mistakes. Einstein's blunders weren't failures. They were more like signposts, pointing future generations toward even deeper mysteries and more profound truths about how our universe actually works. It just goes to show you, sometimes the most important thing a genius can do is ask a question so brilliant, it takes 100 years for the rest of us to figure out the answer.